Okay, so on top of the worksheet, I said, wouldn't be a bad idea for you to attempt these two up here and see if you could get them. We're trying to find a coterminal angle such that, we're between 0 and 360. If you didn't do that, I'm probably going to go through them anyway because they're kind of fair, but this is where we had stopped. So the first thing we would do is say to ourselves, self, that's going to be a lot of 360s. Let's see how many 360s that's going to be. So if we have our nasty little negative 28,549, and that's just reminding me that there's probably some people that need to borrow a calculator. Anybody need one? Anybody else? All right. So we're trying to figure out how many full rotations this can make. Since this is in degrees, we're going to divide. Oh, I definitely hit a button there, didn't I? By 360. And we get that. So normally we'd just say, okay, well, it's 79. Let's take 79 times 360. But this is negative, and we have to figure out how to get it to be positive. So instead of using 79, which would get us closer to it, we're probably going to need 80 to get it to be positive, because it says right here that our theta angle needs to be 0 and 360. Now, it wouldn't be wrong for you to try the 79 first and then add another 360. But just to save time, if we know that, come on, there we go. Approximately that. We should say to ourselves, okay, but if I just go to 79, isn't this still going to be negative? And I need it to be positive. So I'm really going to need to take 360 times 80 in order to get this to happen. So 360 times 80 is going to be 28,000. Ooh, that didn't line up. 800. So let's take our 28,800 and we could just subtract our 28,549. And it's 251 degrees. Which is definitely between 0 and 360. Like I said, it wouldn't be wrong to say, oh, I'll just round to 79, and then you'd realize, oh, wait, I'm still in the negatives here, I need another 360. But if you think ahead about it, then you're going to save yourself a little bit of time. Nope. Alrighty. Oh goodness, look at that. Somebody's having a little fun with us. 4, 5, 6, 7, 8, 9, 10. 4, 5, 6, 7, 8, 9, 10. Divided by 360. Wow, that's a lot of revolutions. So, should I use 126,885 or should I use 126,886 for this one? The 5, yeah, because this is positive, and so but we don't want it to go into the negatives. So we will take 126,885 times 360. Gets us that monster. So we're going to subtract that. And see what we get. And really, if we look at that, we realize, well, the 4, the 5, the 6, the 7, the 8, all going to be gone. So really what I have to do here is figure out 910 minus 600. So what should we use for a coterminal angle? 910 minus 600? 310. And yeah, I probably get the right notation on my red one here too. Oh, this one was phi. So phi coterminal and theta coterminal. 360 degrees. Again, degrees is not what want to use all the time, but we need to remember the things that we know about degrees as we start working towards something that's much more, well, accurate. You know, in math, we like exact answers. So in addition to coterminal angles, there's another special angle that's associated with each and every angle in standard form, and that angle is called a reference angle. And that's the real point of trig is using those reference angles. So a reference angle, theta REF, that's really small up here. I hope you can make out the REF in your notes, is a positive acute angle. Obviously, we would prefer to work with positive angles if we can. We don't want to have to force negatives, but we want those positive acute angles. Now, the reference angle is always the measure of that positive acute angle between the terminal ray and the closest x-axis. It always works as a reference angle. So wherever your terminal ray is and the closest x-axis is your reference angle. Now, why do we use that? Because those reference angles have the same trigonometric functions as the original angle. And that's the reason that we use those reference angles. So down here, we have example 6. For any angle that terminates in one of the 4 quadrants, there are 3 other angles within one rotation that have the same reference angle as that angle. All coterminal angles have the same reference angle. So just because it's visual, here's what we're saying. They give us an angle of 110 degrees, and they ask us for the reference angle. The reference angle is the angle that's formed with the closest x-axis. Well, this isn't the closest x-axis over here. For this terminal ray, they're talking about this one right here. That would be our reference angle. So wherever it lands, we have to kind of think, okay, how do I get that reference angle? Well, a straight angle is 180 degrees. If this is 110, this little chunk right here has to be 70. It absolutely has to be. Just using what we know about angles. And that would be our reference angle. Again, it's an angle that allows us to work with the trigonometric functions that would give us the same answers as that 110, but it's much easier using that reference angle. So that's the reason that we do that, because it's acute. So this one says if beta is negative 265.363, A is draw it. You know, take a peek at it. So stop right there and we'll draw beta in standard form. All right, so we have our initial ray on the positive x-axis. What's going through your mind as you look at negative 265.363? Okay, got to go clockwise. All right, so let's see. This would be 90, 180, not quite to 270, right? So something like that. There it is. It's drawn in standard position. Cool. B. Find the reference angle. Now, to think about this one a little bit different this time, because it did land in the same quadrant as that one, but is the math different? Well, I mean, we could say we still just crossed 180. It's just we want to know how much is left after that 180. So you figure out the math that works for whatever quadrant you're in and say, I know I passed 180 here. I couldn't get all the way to 270, so I need to know how much difference is there between this and 180. It doesn't matter that it's negative. We just need to know what's the difference between those two. So we need 265.363 degrees minus 180 degrees, and that will give us our beta reference. So 265.363 minus 180. And 85.363. I'm just going to transpose those two numbers. 0.363 degrees. There's our reference angle. C. Coterminal angle. Beta coterminal. For 47 positive rotations away. Oh my goodness. All right, so we're going to take negative 265.363 and we're going to add 47 times 360. And that sounds like fun. Let's see what we get. Negative 265.363 plus 47 times 360. Oh, what a fabulous number. 47 positive rotations away from it. Isn't that beautiful? Now, that was C. And D says, convert beta reference, and beta coterminal into DMS notation, round to the nearest second. How many of you have ever heard of DMS notation before? See, this book assumes that all of you learned DMS. Our current geometry book doesn't teach DMS. And it's not a difficult process, but we have to know how to do it. So, first things first, this is definitely not the coterminal angle I would use if I had to think about a coterminal angle. If I were trying to find a nice coterminal angle for this one, does everybody see that it would be this angle right here? That would be the nice one. So that's really the one that we want to use for beta coterminal. We don't want to use this nasty 47 rotations away. So let's figure out what the real beta coterminal that we would want to use would be. And I'm just going to switch colors here so that you know, hey, this is really the one that we would want. And that angle is going to be found just by saying, okay, all the way around it is 360. So if I subtract this monster that I just had, then that should give me my coterminal angle. So if I take 360 and subtract 265.363, that'll give me a decent coterminal angle, not that huge nasty number that we had right up there. So let's see, 94.637. Put it up here so everybody can see it. So when we put this into DMS, we don't want to be working with this 16,654 business. That's not what we want. We want the nice stuff that we would actually want to use. So how do you do DMS notation? DMS is degrees, minutes, and seconds. I don't have enough space here to do that, so I'm going to go on the page. Hopefully you've got some writing space somewhere. Degrees, minutes, and seconds. And the notation is going to be whatever we have for degrees gets a little bubble. Whatever we have for minutes gets 1 strike. And whatever we have for seconds gets 2 strikes. You can think of it as like feet and inches as you go through there. But what this really does is it uses the system based on degrees. And that system of degrees tells us if we have a degree and then we have points behind it, maybe there's a better way to label all of the nastiness behind than just saying 26.375 degrees. So what we do is we convert it into minutes and seconds, and it really works the same way as hours, minutes, and seconds. It does. So whatever you have for degrees, there are 60 minutes in 1 degree. And whatever you have in seconds, well, there's 60 seconds in each of those 60 minutes, so there are 3,600 seconds in 1 degree. So like I said, I usually just think of this as like the clock, you know. We're talking about minutes, seconds, you know. Just think of it that way, and you'll be fine. So what this is really about is, can you convert the back portion of a degree? So let's just say our answer came out to 3.437 degrees. That's just degrees. That's not DMS notation. So when they ask us to do DMS notation, we're going to say, okay, it's 3 degrees plus something minutes. Well, to find those minutes, all I have to do is take this decimal times 60. That's all I have to do. So if I take 0.437 times 60, that will give me 26 minutes. Still have stuff left over there, right? After the 26. That's for the seconds. So now if I take 0.22 times 60, I'll have it in seconds. So this would be 13.2 seconds. So again, you can think of this as hours, minutes, and seconds, but it's DMS, degrees, minutes, and seconds. So you're always looking at what's after the decimal, because this was degrees. This is a portion of degrees back here. What portion is it? And we represent that with minutes, and we represent it with seconds. So that's the DMS notation. So let's go back to the ones they wanted us to do now and convert those into DMS. So for D, we want that original beta, but we want that in DMS notation. So that's going to be negative 265 degrees. But now we have the nasty decimal part. So we're going to take 0.363 times 60 to get the minutes. So 21 minutes. But I still have a decimal after that, which means I also have some seconds. So I need 0.78 times 60 for the seconds. So if we wanted to round, we'd say about 47, but we're going to go ahead and write 46.8 seconds. That one, so that it's exact. So that's in DMS notation. Next one they had there was beta reference. Well, here's our reference angle right here, 85.363. So 85 degrees, 0.363 times 60. Wait, we already did that. Right up there. Then 0.78 times 60, which we already did. So there is the reference angle in that DMS notation. What's the last little one there? Beta coterminal. That's the reason I did the red one. I don't want us using that big monster. So beta coterminal, well, we've got 94.637 degrees. So 94 degrees, 0.637 times 60. So 38 minutes. And 0.22 times 60, 13.2 seconds. And now those are all in DMS conversion. So, like I said, I just always think of it as hours and minutes and seconds. It works exactly the same way, and then it makes perfect sense. But they assumed we taught you that in geometry. Our geometry book does not have that information in there. So, not difficult, just the first time you saw it. So, I'm saying that. I don't want to sway you one way or another. I want to know, how do you feel about DMS conversion? Give me a 43210 on how you feel about using this DMS system. It's new, so some people are still a little uncomfortable, but most people are getting it. That's good. It's brand new. You should be honest with me. For each of the following angles, theta, find the coterminal angle, alpha, such that alpha is between 0 and 2 pi. Pi, where did that come from? But we're going to talk radians. We are. And you did a little radians in geometry, but again, my guess is we've probably forgotten a little bit about radians. So, we did a little conversion yesterday. I'm going to show you a little bit more today. When we use angles, we generally think in terms of degrees because that's the first thing we've ever learned. It is not the most accurate way to measure angles. Radians is much better. So with radians, if we start where we're supposed to on the positive x-axis and we go across for a 180 degree angle, that is actually pi radians. And notice I don't put a label on that. And that's because if we have an answer that has pi in it, we assume that it was in radians. It's just the standard way to do it. You may occasionally see something that says RAD behind it, but normally if it doesn't have a label, it's because it's radians. So if it takes us 1 pi to get over here, how many does it take us to make it all the way around? 2 pi. 2 pi. And yesterday I gave you the quick and dirty example there where if we have something in degrees, we're going to have to multiply that by pi over 180 degrees. And it's just the formula that we use to make it easier. And if you're saying, well, why wouldn't we use 2 pi in 360? Because it reduces to pi over 1. Why not use the smaller conversion when you're going through it? So 180 degrees is pi, 1 pi. 360 is 2 pi. Now here's where it gets weird, because that's what you saw in geometry. And here we're also going to see these as numbers, numerical representations. So if we see 3.142 as an angle, we're supposed to know that's 1 pi. And if we multiply that by 2 and get 6.283, we're supposed to know, hey, that was in radians. If there's no degree bubble, it's in radians. So pi, 3.142, 2 pi, 6.283 radians. And again, radians will not always be labeled for us. If we look for a bubble and it's not there, it's in radians. So, a little more background on our fabulous radians. Back to this again. And here's what it says. For each of the following angles theta, find the coterminal angle alpha such that we're between 0 and 2 pi. Then find the reference angle beta for each angle. But all of these are given in radians. So if they're in radians, we're not going to use 360 degrees to convert all of this stuff. With what we just had, what should we use instead of 360 if we're going to talk about radians? 2 pi. 2 pi is 1 full rotation. So the math is done the same. It's just that we're using different representations for it when we're involving pi. So look at that one. 46,365 pi over 7. Golly. Well, I'm thinking that's more than 1 full rotation, so let's figure out what it is. 46,365 times pi, and then we're going to divide that by 7. Whew. That's what the angle is. Now I want to know how many times is that going to go all the way around. So I have to divide that by 2 pi. So divide by parentheses 2 times pi. So this came out to 20,808.563, and we are dividing that by 2 pi to see how many rotations this is going to take. So we've got 3,311.786 or so rotations. Well, now I need to use that to figure out what would the coterminal angle be for this angle. You know, what would land between 0 and 2 pi that would give me the same stuff? Well, that means I've got to take this monster right here. And I've got to subtract enough rotations out of this to leave it as the smallest positive value that I can possibly get. That's why that was so important, because that tells me not only is it going to go all the way around 3,311 times, but there's also going to go past it. You know, it's going to go past it a little bit. So what I want to do is I want to subtract 3,311 full rotations, but not in degrees, in radians. Problem. These are fractions. And with fractions, you need a common denominator. So let's see what we have so far. 3311 times 2. Whoops. 3311 times 2. There we go. That's better. So 46365 pi over over 7 minus 6622 pi over 1. Oh, we're so close. Common denominator. Multiply by 7. Top and bottom. 46, 365 pi over 7 minus. Oh, let's take our 6622 times 7. 46, 354 pi over 7. So 46, 365 minus 46, 354. Oh, well, really, all we would need to do is 65 minus 54. That's going to be 11 pi over 7. That is the coterminal. And I think they wanted us to use a different Greek symbol here. We should find the coterminal angle alpha. It's a good thing that's most of the work for this problem. That's a lot of stuff. Then find the reference angle. Oh my goodness. All right, the reference angle, easiest to do with a sketch. Oops, put that back on here. All right. So, 11 pi over 7. This is 1 pi, and this is 2 pi. The easiest way to figure out a reference angle is by making a visual. And I know we write it as 11 pi over 7. That's how it's supposed to be written. But here's how we need to think of it. We need to think of it so that we can find it as 11/7 pi. And realize that that's going to go in there 1 and 4/7 pi times. So you really switch that into a mixed number so you can find out where this angle is at. So now, I would start here, and I would go 1 pi, and then I would go 4/7 of the way to 2 pi. Well, 4/7 is a little more than half, because 3.5 out of 7 is a half. So I'm supposed to go a little more than a half, and that's where it would be. So if this was 1 and 4/7 pi, and all the way around is 2 pi, how much short are we? 3/7. That would get us all the way to 2. So 3/7 pi would be our reference angle, but again, we don't write it that way. We write it as 3 pi over 7. And I think they had a different way to do that. Then find the reference angle beta. So once we've found that coterminal angle, the rest of this really comes from thinking through a sketch. You know, this is 1 pi, this is 2 pi. How much do we need to close the gap? And go from there. All right, up here. Another monster. Ugh. Well, first we got to figure out how many rotations we're talking about here. So let's see. -789,637 times pi divided by 11. Whew. All right, we got that. What do we do next? What was step 2 in this one over here? Divide by 2 pi. We need to know how many times this bad boy is going around. Divide by parentheses, 2 times pi. Oh, not that would mess that up. At this point, it's really important to have it as the fraction as you go through it, because that's showing the fraction way that we write radians. This part, obviously, we're going to be having some nasty decimals as we go through it. So this really has to be a mixture, Cassie. It really does. All right, so that's how many times this is going to go around. Yikes. So negative 35,892.59091. But this one was negative, and we want a positive answer. So what should we use when we talk about those rotations? 35,893. Yeah, we need the 3 to tip it over and make it positive. So we're going to need 35,893 times 2 pi for this one. So we have, oh, we need some smart word. I know you're mad at me because I've got recordings going. Negative 789,637 pi over 11 plus, might as well multiply that out right now. 35,893 times 2, 71,786 pi. Oh no, that didn't go far enough. Did I slip when I entered this in? 3311. Yeah, it should have been 3311. I slipped when I punched it in. Oh no, I'm just thinking ahead to the next step. Alrighty, so we've got this over 1. That's why I was thinking ahead to the next step already. So now what? Common denominator, yeah, as if we didn't do enough with the big numbers already, but now we're going to have to multiply top and bottom by 11. Won't that be fun? 71,786 times 11. Whew. Yikes. All right, so negative 789,637 plus 789,646. All of that for 9 pi over 11. A lot of good math there. And that one they wanted us to call alpha. Going back up to the top, those coterminal angles, they wanted alpha. Okay, now I've already got a sketch over here. And I need you to start thinking in radians. So instead of thinking 9 pi over 11, what should you think? 9/11ths pi. So think of where 9/11ths pi will take you. And now what's going to finish up getting it to the x-axis? 2 pi over 11. 9/11ths pi is not all the way over. It's short by 2/11ths pi. So 2 pi over 11. So reference angles are always with that closest x-axis. Oh, we still have 2 of these to go. Wonderful. All right. Theta equals, we have there 14,998,763 pi. Seriously? Okay. What do we do? Yeah. 14,998,763 times pi divided by 2 times pi. All right, so should we use 7,499,381 or should we use 7,499,382? 1, because it's already positive. So 1,499,8 .763 pi minus, and 2 pi times 7.874. 99381 times 2 pi. 99381 times 2. 1499876 pi minus 1499876 pi. Hey, wait a minute. That's 1 pi. Well, so we're supposed to come up with the coterminal angle. That's this coterminal angle right there. It's pi. Reference angle. Isn't this on the x-axis? So this we say does not have a reference angle. This is a special angle. Pi over 2, anything that really lands on the x or y axis, those are called quadrantal angles. So they don't get a reference angle. They are fantastic little angles in their own right, so they don't get a reference angle. They have really beautiful symmetry that works with them as you go through. So at least we don't have to do a second. What we did was we did the math here so we could see how many times it's going to go around. And then we said, okay, because this is positive, if we rounded this up, we're actually going to get a negative answer. We don't want that, so we used the rounded down. And we've got the original minus all of those rotations that we said we had to use times 2 pi. And that's what gets us down to that coterminal angle. It lands it in the same place. And then, like I said, if it lands on something nice like pi, then it's not going to have a reference angle. But in the other ones, we had to figure out by radians how it was going to go. Well, as if that wasn't bad enough. Look at D. There's no label. So is it degrees? It is not. If there is no label, it is in radians. There is no label. This is already in radians. That means somebody already did the multiplying times 2 pi. You know, the multiplying times 2 pi thing is already in there. So in this one, we had to multiply by pi before we divided by 2 pi. It's just going to save us one step. We're just going to take that number and divide it by 2 pi and figure out the revolutions. So 36142.51 divided by parentheses 2 times pi. Boom. So 5,752.259122. Okay. So it's positive. What should we do? Do we do 5752 or 5753? 52, right, because we want it to still be positive when we get done. So 36142.51 minus 5752 times 2 pi. That gives us what we need. Question 36142.51 minus parentheses 5752 times 2 times pi. Again, I'm going to write radians as a label down here because I want you all to remember that, but that's what that says. Since there's no degree bubble, this is radians. I want to make sure that when it's in your notes, you know how we got that. So now, how on earth are we supposed to figure out a reference angle for 1.628? Back to this one. .628. We haven't dealt with this. We haven't had to do this before. So the first question you'd have is, well, what's the number that goes with the positive y-axis up here? Well, it's half of this. So we take 3.142 and divide it by 2. That's this one. So we're going a little farther than that, right? So how are we going to get this reference angle? Yeah, just subtract 3.1417, blah, blah, blah. So we can just use pi on our calculator. Second pi minus 1.628. And there's our reference angle. 1.514 radians. All right, Cedar Home, if the rest of the notes are going to take this long, we're never going to get through 4-1. They don't. These are kind of the challenge problems right here on this page. And it's not necessarily, I don't think, because it's the hard stuff. It's just that the numbers are so nasty as we go through that. So, well, at least we can say we started 4-1. We could fill in a box or two. Come on. There we go. Pre-calc, section 401 is about angles and their measures. That tells us everything we just did was precursor information. It was stuff we were supposed to know before we got started on chapter 4. So those things that we just did, the understanding of those, incredibly important to working with the trade. So when we get done, we want to be able to work with the DMS measure, and obviously it's not a tough conversion thing to do. We want to be able to make conversions not only from degrees to radians, but also go backwards, vice versa. And then find arc length and make connections between angular and linear motion. And I'm going to have to say, I hope you can finish that worksheet now. That's probably the only homework I'm going to be able to add for now. Oh, again, this was from geometry. If you have something in radians and you want to convert it, you're going to multiply it by 180 degrees over pi radians. So it's just working backwards with what we were doing when we were taking degrees and making them radians. This is taking radians and making them degrees. I think that's probably the last thing. Oh no, you won't be able to do 21 to 26 because we didn't do the formula for arc length yet. All right, well, do what you can. Sorry I can't give you more homework. You know, get through what we get through. Yeah, there's a reason we had 4 days on this section.